Good morning, guys. This is Mr. Birdie. I am just going to walk you through how I would go about doing my PNAS project. Okay, so what's been on my mind has been COVID. Currently, if you're watching this in the future, I currently have COVID and I'm on like day 8 of isolation and it's driving me crazy. All right, but what I wanted to just learn more about COVID and when will I be safe for others to be around. Okay, so I started on this research. I Googled COVID and transmission, I believe, in the PNAS search bar. Okay, I got a whole bunch of articles. I'm going to show you how I would like you to go about it. I really went down the wormhole. Okay, and I think you should too. And you should dedicate some time aside to read a lot and find a cool study that you want to do. Okay, so I'm going to walk you through how I did this. Um, Basically, I started on this study. Okay, and this isn't the one that I actually am going to end up doing my PNAS on. All right. It's basically about identifying airborne transmission as a dominant route for the spread of COVID-19. And they're going to talk about how mass, right? They said this, that our analysis reveals the difference with and without mandated face coverings represents the determinant in shaping the trends of the pandemic. This was published on June 30th. Okay. Other mitigations, all this other stuff are insufficient by themselves in protecting the public. So the order to wear masks would have been the most important, even more important than shutting stuff down, right? Way back in March, okay? So anyways, I read this and it was fascinating. You can hear my children screaming downstairs in the basement. I haven't seen them in a while. Okay, isolation is brutal. Okay, but anyways, this was all fascinating. I read this and I thought it was really cool where it talks about microorganisms and viruses and how long they can survive at different temperatures. And I had to look up the term atomization, right? And this is all going well until I got to this, viral shedding, because this is actually what I am intrigued in. How long will I shed virus for, right? So I read this line. In addition, viral shedding is dependent on the stages of infection and varies between symptomatic and asymptomatic carriers. The recent findings, 16. This is where I went. I clicked on 16 and I got the reference for it. Well, neither one of these links brought me to it. So I just copied this whole thing and it got me to, oh no, not this. Oh boy. Oh boy. Okay, I guess I'll show it to you that how exactly I got here. So I'm going to copy this deal and we're going to go down the wormhole. That's what I want you to do. Oh geez, my kids are really screaming. So here I'm down the wormhole, temporal dynamics and viral shedding. This is a study that I ended up doing my PNAS on, okay? And it ends up being fascinating, okay? They looked at 94 patients with laboratory confirmed COVID-19. This, by the way, this was published, August. Wow, this is published about a month ago. Okay, so anyways, I'm not going to bore you with all the details, but I just want to show you the process of doing a PNAS, okay? I eventually got to this term serial interval, right? There's a lot of terms on here that I'm not familiar with, right? I've got to figure out which ones are pertinent to my understanding of the study and which ones aren't. And this one popped up a lot. So what do I want you to do? Go down the wormhole. And what does that mean? Google. Okay, so you can see I had to Google serial interval because I wanted to see what exactly they mean. And here it is. The serial interval in the epidemiology of communicable diseases refers to the time between successive cases and a chain of transmission. I still had to do further reading on it, but I can explain it to you now that basically the serial interval is if I got it and I spread it to my wife, what's that time period? Okay, so they're going to focus on that. And their first graph that I would present as part of my project is here. And you need to spend some time here, right? But I read first. I read a lot first. And then this starts to make, actually, here's a tab. My kids are still screaming in the background, okay? But here's the deal. Hypothetical scenarios. This is their deal, right? And they'll talk about if the serial interval takes this long, and here's symptom onset, that if the serial interval equals the incubation period, okay, then right when you get your symptoms, you're contagious, okay? Maybe perhaps the serial interval is longer than incubation, right? That here's your serial interval, and it's real long, right? You can kind of see this distribution of infection onset. So if it's longer, then, well, so when are you most infectious is what this graph shows in relationship to this hypothesis, okay? Here's like the scary one, right? And and this is like COVID-19, I believe, right? Is that the serial interval is less than the incubation period. And the study's going to go on and talk about what this means. Okay, but the serial interval is actually, if you are contagious to another person and you would pass it to another person in your chain of transmission before your symptoms onset. So the serial interval is shorter, okay, than when you gave it to the secondary case. So what does this mean? It means that quarantining and shutdown isn't going to be the best if we wait until symptoms onset, which is why you have to quarantine if you're exposed to a person that's COVID positive, okay? Look at SARS in 2003, a much deadlier virus, but the good news with SARS is it had this really long serial interval period, which meant symptoms showed up before you were contagious, okay? Days from symptoms onset of primary case, this is when you were your most contagious. Well, then what's most effective in that isn't mask, it's isolation and quarantine. Once you get symptoms, stop going out because you can spread it to people. All right. And maybe this is a lot, but this is how the PNASs have to be. You have to spend time on them. You've got to read closely and figure out what these graphs are all telling you. Okay. So I thought this was fascinating. Okay. Going back to, I think I get back to article page. Here it goes. I'm gonna click this. Okay. Just more like, how do I do this? I'm going to read. It's all fascinating. It really is cool. These are really cool graphs that took some time for me to understand. I'm not going to explain them to you because that's the point of this presentation. Instead, when I click on this and I read a lot about it, it takes me some time to figure out what's going on. And what seems to really matter is the y-axis CT value. I don't know what the CT value is. So I actually had to get to like 3 different tabs and 3 different searches until I found out, like, okay, CT values are important in PCRs. I had to read about how they did PCRs. And, oh, sorry, the definition of CT value isn't quite here. I thought it was going to be on this tab. But basically, CT around 35 is borderline for true detection of DNA in the background of everything else. Okay, so how long can we detect the virus for? Well, these guys, I believe, use a CT of 40, that after underneath 40, they just couldn't detect it, okay? All right, so what's the point? Why do this? I want to show you that all your information, you might be reading PNASs, but you're going to have to leave PNAS to find some background terms that the researchers use every day of their lives in their working career. You've got to learn some of those and define them to us, okay? So 2 terms I'd have to define: CT value and serial interval, because I honestly, I never took a class on epidemiology. I had a chapter on epidemiology in one class I took. Okay, guys, that's it. Thanks for joining. I hope this is an effective one for many years to come. See you, kids.